Welcome back. In our last lecture, we introduced Darcy's law and how it describes how water flows through porous media as a function of hydraulic conductivity, cross-sectional area of flow, and the hydraulic gradient. Now we're going to look at a special case of Darcy's law as we apply it to flow of water through layered systems. What do we mean by a layered system? This is a fairly typical cross-section of a hydrogeologic unit. You'll notice that there are many horizontal layers. This has to do with the manner in which most soil deposits, or most soils are deposited. They're often put down in thin layers, and over time you have alternating layers one on top of another, and you do get some faulting and some upheaval, things like that, but in general we typically have a lot of flat, relatively horizontal layers woven together. And as a result of this, it's easier for the water to flow horizontally than it is vertically, which is why in most aquifers, well, pretty much all aquifers, the hydraulic conductivity in the horizontal direction is different than the hydraulic conductivity in the vertical direction. And in our next lecture, we are going to look at Darcy's law in multiple directions a little more carefully. When you're dealing with layered systems, one of the things that we frequently encounter is the need to simplify our layered system and represent it using more of a holistic, simplified representation. For example, suppose we have three layers of soil or rock shown like this, and we want to simulate flow horizontally through this system. In reality, if the hydraulic conductivities are different, the water is going to naturally partition itself to where it flows. Most of the water will flow through the layer with the largest hydraulic conductivity and with the largest thickness. Both the thickness and hydraulic conductivity together form what we call transmissivity, which we'll talk about in a later lecture. But there are times when we want to take something like this three-layered system, and apply Darcy's law to it, just as a simple one-dimensional left to right or right to left flow system, or even a vertical. Maybe we want to simulate how water flows vertically. Perhaps the heads vary from top to bottom. And it turns out there's a way you can kind of aggregate these conceptually into a single unit made up of multiple layers and come up with an equivalent hydraulic conductivity that you can then apply to the layered system as a whole. One application of this is when you're doing a numerical model. Let's say you have multiple layers in your geology that correspond to a single grid cell or a single computational layer in your model. We want to take those multiple real-world layers and just come up with an aggregate or representative hydraulic conductivity that represents the system as a whole, and have that hydraulic conductivity then assigned to each cell in the layer of our computational grid. So how do we do this? Let's go through a quick little derivation. It's actually fairly simple. We're going to start out by looking at flow parallel to the layering. So in this case that would be parallel, in this case would be horizontal. And so for this case, the following must hold. We're going to make some assumptions here to drive our derivation. Number one, the head loss is the same through each layer. Now, in order for water to flow, let's say from left to right through this layered system, there has to be a high head on the left and a lower head on the right. So, and that head difference is going to be felt in an identical fashion for each of these three layers. Since the head loss is the same in each layer and the length of flow from left to right is the same, then by definition the hydraulic gradient has to be the same. So that's why we write I1 equals I2 equals I3. Now, one thing that will differ is although the head loss is the same, the hydraulic conductivities are different, so the flow rate is not going to be the same, but the head loss will be the same. And we're also going to assume that the total flow through the layers equals the sum of the individual flows. So Q1 would be how much water flows through layer 1. Q2 would be the amount of water flowing through layer 2, and Q3 would be the amount of water flowing through layer 3. We add those all up together and it represents the total flow rate through the system. Pretty simple assumption there. Therefore, the total flow is equal to Q1 plus Q2 plus Q3. And if you assume, now what we're doing right here is we're applying Darcy's law. Remember that the flow rate is equal to the velocity times the area. Now we are going to assume that the width, and by this I mean the width perpendicular to the screen, so not X and Y, but or not vertical or horizontal, but the opposite direction, is a width of 1. So the cross-sectional area of flow would be the height of each individual layer times 1. And then the total, if we're looking at the system as a whole, if we take the velocity times the total area, which is h, the total height times 1, that's going to be equal to V1H1 plus V2H2 plus V3H3. And then we are going to apply Darcy's law and replace each V with Ki. Remember, one of the forms of Darcy's law is V equals Ki. And so on the left we have K equivalent, I equivalent. So this would be a K equivalent means this is the equivalent hydraulic conductivity for the layered system as a whole. And then K EQ IEQ times H is equal to those terms on the right. We've just replaced V1 with K1I1, V2 with K2I2, and so forth. Now, we've also established that the I's are the same. So IEQ equals I1 equals I2 equals I3. So we can just replace them with I and then divide by I and essentially just get rid of the I terms. And so now we have K equivalent H. The K equivalent times the entire thickness is equal to K1H1 plus K2H2 plus K3H3. Now if we simply divide both sides by H, we have our solution. The equivalent hydraulic conductivity is equal to this expression on the right, and if you can put that into a summation form. So basically, if you sum the individual thicknesses times hydraulic conductivity, which is also the transmissivity, and divide that by the total thickness, you get an equivalent hydraulic conductivity. And at that point, you can then use Darcy's law with this hydraulic conductivity to represent that layered system as a single unit. And so Q through the entire system would be KEQ times the cross-sectional area times the hydraulic gradient, and you can apply Darcy's law directly. Simple as that. So now let's look at the other case. There are two cases here. Now instead of the water flowing parallel to the layering, we're looking at the water flowing perpendicular to the layering. So in this case, maybe the head on the left and right doesn't change, but the head at the top is different than the head at the bottom. So if water is flowing up like this, it would be like an artesian system where you have a pressurized unit pushing water up through some layers. And it could go either direction, but the point is we have a head differential that pushes the water perpendicular to the layering. And so now we're going to again come up with a different equation to develop an equivalent hydraulic conductivity that we can apply to this system as a whole. So now we have a different set of assumptions. For this case, the following must hold. One, the flow rate is going to be the same through each layer. When we're flowing parallel to the layering, as I mentioned, most of the water is going to go through the most permeable layer. Now in this case, just because of physics, the water has to go through all three layers, and therefore the flow rate is the same. And since we have different hydraulic conductivities in each layer, the layers with a low hydraulic conductivity, it's going to take more energy to push the water through those layers. So you're going to have a larger head loss in the low permeability layers versus the high permeability layers. And so whereas in the first case we had the same head loss, now the head loss in each layer is going to be different, but they are going to add up to the total head loss as you go from the top of the system to the bottom of the system, or vice versa. With these assumptions in mind, we can say the total Q is equal to Q1 equals to Q2 equals Q3, and therefore the velocities, the Darcy velocities, would be the same, and therefore we can just apply Darcy's law, V equals Ki, and that Ki value would be the same through each of the three layers. And remember that the hydraulic gradient is equal to the change in head divided by the total thickness of the system. The change in head through the whole system would be the sum of the individual heads, delta H1, delta H2, delta H3. And therefore, the head loss in each layer, we can represent that a little differently. So the head loss in layer 1 is equal to the thickness of layer 1 times the hydraulic gradient. Remember, the hydraulic gradient is how much the head changes over a certain length. And so if you multiply that gradient times a thickness, you'll get how much head loss occurs in that layer. And the head loss in layer 2 is the thickness of layer 2 times the hydraulic gradient of layer 2. And the head loss in layer 3 is the thickness in layer 3 times the hydraulic gradient of layer 3. So now what we are going to do is we're going to jump back and look at this equation right here. And if you just look at this first term, K equivalent delta H over H equals K1 times I1, if you solve that, if you divide by K1, you can then derive an expression for I1 in terms of these other coefficients. And if we look at the next slide, that's what we're doing here. And then if you do the same thing for I2 and I3, you get this set of equations. And then remember the last equation on the previous page, delta H equals H1I1 plus H2I2 plus H3I3. So if we plug these three terms in for I1, I2, A3, we come up with this term. Finally, if we divide both sides by delta H and solve for K equivalent, we now come up with this term. This one's a little trickier than the other one, but in the end we have another very simple equation, and this can be represented very simply in a summation form as the equivalent hydraulic conductivity is equal to the sum of the heights, or the entire thickness of this layered system, divided by the sum of HI over KI. So now we have two very simple equations for calculating an equivalent hydraulic conductivity to treat a layered system as a unit so that we can apply Darcy's law. As long as we calculate the correct K equivalent, we can plug that right in and do some really interesting things. And we have some in class, some exercises we're going to go through that illustrate this, and we can gain some really interesting insights into a layered system by calculating these equivalent hydraulic conductivities in each dimension and looking at how sensitive they are to the thicknesses and the hydraulic conductivities of the individual layers.